I'd like to just start with a couple of introductory notes. First, I'd like to echo David's comments from his talk that it's great being here in Santa Cruz. For me personally, it's really helping drive home the reality that I'll be coming here in the fall to work with Gene Brody and Charlie Conroy on a mixture of stellar population models and globular cluster systems around nearby galaxies. And the other thing I'd like to point out is the change in the title of my talk. The change is meant to reflect the fact that in this talk I'm going to be divulging some results on recent work that has rounded out my PhD thesis on the stellar mass properties of Virgo cluster galaxies. Now, despite the change in the title, our goal remains one and the same. We wish to ultimately drive improvements in galaxy formation models by obtaining constraints on the evolution and formation of cluster galaxies. So about 80% of my PhD thesis, I would wager, is driven by the Shiver survey, which Stefan just talked about, so I won't spend too much time on this topic. But salient points about it, which I would like to express, are that this work that I'm presenting today builds on the optical and near-infrared photometry of these galaxies that we have in the Virgo cluster, as well as their optical spectra. So we have this photometry and spectra for a large sample of galaxies from the cluster. The sample is shown here on the right. So this is the distribution on the sky relative to the full VCC catalog. And the color points are the galaxies in our sample. The legend shows you we have a really representative mixture of morphologies in our sample. And the fact that we cover such a significant range in cluster-centric distances means we probe a significant range in galaxy densities. So much work has been done between Stefan and I so far on the Shiver survey. Here's just a quick executive summary of what we have accomplished. Back in 2011, we put out a couple of papers on the color and color gradients, as well as the transformations of those colors into mean age and metallicity measurements, and looking at things like trends in those properties with morphology, galaxy structure, environments, so on and so forth. And then in 2012, we revisited our data on a per galaxy basis, coupled to the shapes of their light profiles to try and gain some insight onto the evolution of the disk galaxies in our sample vis-a-vis this phenomenon of stellar migrations that was, I guess, largely started by the Washington group. I would wager that a key result from all this work is our constraints on the gradients in color, mean age, and metallicity for different galaxy types in this sample. And what we have been able to show is that these color gradients, here W means weak, S means strong, are largely driven by variations in metallicity through these galaxies, throughout these galaxies. The mean age of the stars doesn't seem to change so much as you move from the center to the outskirts. Okay, well, so that work that has been done so far concerns measurements of mean age and metallicity, and basically that gives us a handle on what has been the shape of our galaxy star formation histories and as well as their enrichment histories. How can we go further with the data from the Shiver survey? Well, recently we've been concentrating on the stellar mass properties of the galaxies in our sample, and just loosely speaking, we can think of that as kind of putting some constraints on the overall efficiency, the history of star formation efficiency within our galaxies, as well as kind of the amplitude of the star formation histories. But more deeply, what we wish to address in this investigation was, what is the budget of stellar mass amongst Virgo cluster galaxies? How are the galaxies within Virgo actually distributing the stellar mass throughout their volumes? And finally, and somewhat excitingly, is can we use the combination of stellar masses and dynamical masses from the optical spectra that we have in Shiver to make some informed results or insights onto the relation between stellar mass and halo mass that people like Risa Wexler, Charlie Conroy have been studying for years. Okay, so first let's start off with a description of how we go about measuring stellar masses. Now, because we want to look at stellar mass both amongst galaxies and within them, we have a large number of computations to perform, and because of its efficiency, we then turn to the method of using calibrations of mass to light ratio versus color in order to measure stellar mass. But as opposed to what's been traditionally done in this respect, we don't a priori restrict ourselves to any one color. Okay? We'll look at all colors available to us from our shiver data. And the reason we want to do that is because it will help give us, it will help combat against any kind of biases that we have within the calibrations themselves due to the priors which underlie them. So this plot here shows various calibrations, some of our own making. The top 3 are ones that we've created ourselves. The bottom 4 are from the literature. And so it plots mass to light ratio in Sloan I-band versus various sets of optical and optical near-infrared colors. And so the process that we do is we literally measure the colors for a galaxy when we put them in each one of these planes, and then through each one of those colors we gain a measurement of a mass to light ratio. We can then average them together to get some sort of representative value for that galaxy. What's interesting about when we look at these different color trends within these figures is the amount of discrepancy between them. Okay? In your optical near-infrared colors, you're looking at almost 0.6 dec at certain points in difference between what different stellar population models will give you. So this raises the issue of what are the systematics in measuring stellar mass for galaxies. And here, this is just a blow-up of the panel, the top right panel from this figure here. So what we're looking at again is mass to light ratio versus now G minus I color. And in the bottom panel, I show the difference between the various lines in the top panel measured with respect to the calibration from Zebedee 2009. And so what we can see is at the worst, the difference between model predictions is about 0.3 dec level, which is kind of what we've been hearing about over the last few years. It's not too surprising, but needless to say, but it's still important to recognize these systematics when undertaking this type of work. And so the other thing, though, is that beyond stellar population models, there's various aspects related to methodology that can also drive differences in your stellar mass estimates. For instance, whether you adopt our approach of fitting to calibrations of mass to light ratio versus color, or if you do traditional SED fitting. We can get differences in the results there, largely driven by the priors in the calibrations. As well, the number of spatial dimensions over which you estimate stellar mass can have a significant effect. Most times that this kind of work is done, you're weighting your stellar mass estimate by light. And that creates the opportunity to miss stars within galaxies that are either shrouded by dust or outshone by bright stars. And so if you do things on a 2D basis, pixel by pixel, you can more accurately recover that missing stellar mass. Now, aside from the systematics, and by the way, this level of discrepancy is amongst the best between the color panels that I showed you in the 2 slides ago. But leaving aside the issue of systematics for now, what is the intrinsic accuracy that we might hope to which we can hope to estimate stellar masses based on stellar population models? And this figure here shows an experiment with mock galaxies where on the vertical axis we're plotting the fitted stellar mass versus the input stellar mass for various combinations of observational constraints. So we have UV through SED sampled with UV through NIR near-infrared filters in the top 2 panels. Bottom 2 panels are restricted to optical near-infrared and just optical colors. The percentages here refer to the amount of noise that was introduced into the spectra. But the take-home point from this figure is that really we don't see much change in the scatter amongst the different combinations of noise and observational constraints. And so this is interesting because if you believe that whatever stellar population model you're using to analyze your galaxies is actually representative of them, then we might do just as well restricting ourselves to G-I colors as opposed to a fully sampled SED. And that carries various advantages, like optical data can probe a lot further out into galaxies, so we can hope to measure stellar mass density profiles to much larger radii just on the basis of optical colors alone. Okay, with that, let me just give you a quick overview of the results that we've obtained so far. I'll start with the stellar mass function of the Virgo cluster, which to our knowledge has never been done before. Lots of studies of the luminosity function, but not in terms of stellar mass. And so here in purple, we show the mass function that we've obtained by fitting to the G-I colors of our galaxies measured within an optical radius, R23.5. And we're comparing against other Schechter functions fitted to various surveys, SDSS, 2MASS. Here we have the gamma survey. And what we see is in the local universe, there's a very good correspondence between what has been obtained amongst the various surveys with a low mass slope in a range of 1.2 to 1.1 and characteristic mass within a scatter of 0.5 dec. Then when we compare the parameters that we get for our Virgo mass function, we see that the dwarf regime seems to be reproduced both in the cluster environment as well as largely field environment. I should have mentioned that, is that these studies largely target the field. But the difference, one difference is that the characteristic mass is somewhat larger in the Virgo cluster than in the field. And so what this tells us is, as we would expect, cluster environment preferentially hosts more massive galaxies than the field. And this has been seen in other recent work of mass functions across many environments by a paper just released this year by Rosa Calvi. Okay, from there we can then look at the distribution of stellar mass within galaxies as a function of their radius. And why we might want to do that is because the structure of galaxies has been studied, ad nauseum over the past, 20, 30 years by the likes of people, John Cormody, so on and so forth. But it's always been done in light. Whereas stellar mass is the more fundamental quantity. It's the one that we would like to compare against theoretical models. So to try and drive that comparison, let's look at what we have for our Virgo sample. So on the left here, we're plotting the stellar mass density profiles versus logarithmic radius, which will highlight the inner regions of our galaxies. And then the outer regions we see by plotting in just linear terms. And now the galaxies in our sample have been binned according to surface brightness. And what we find there are some interesting trends is basically the central density, central slope, and the outer shape of the profiles seems to, amongst the parameters that we've explored, mind you, seems to correlate most strongly with surface brightness. And so what we infer from this is that the mass to light ratio within galaxies doesn't vary too much, which agrees with our previous results on the age gradients. Okay, final bit of news from this recent work is our exploration of the relation between stellar mass and dynamical mass for our galaxies, both measured within the optical radius of our isophoto radius of our galaxies, R23.5. And so here on the left, I've plotted stellar mass versus dynamical mass, points color-coded by morphology. Here in the top left corner are estimates of our various systematics related to either the x-axis or y-axis quantities. And what's interesting is we see amongst the earliest type morphologies is this nice trend where things sort of cluster about the 1-to-1 line at around 10 to the 9 solar masses and then bend away as we go to higher dynamical masses. But even more interesting than that is when we bin the data by dynamical mass and we measure the scatter in stellar mass, we find that it changes remarkably as a function of the dynamical mass. Okay, and so this really kind of, I think, hits home. If we can think of this, these plots as kind of a proxy for the stellar mass-halo mass relation, then this is very informative to people who do theoretical abundance matching, like Reese and Wexler, because what is commonly assumed is that the scatter is constant as a function of dynamical mass. Okay, last bit of results is what sets the position of a galaxy within that plane of stellar versus dynamical mass. Here we're plotting the ratio of m star over m dynamical versus various structural parameters from the Shiver survey. And what I'd like to draw your attention to is the panel on concentration. We detect a statistically significant correlation amongst the early type galaxies in our sample, whereby as you go to higher concentrations, the fraction of dark to stellar matter increases. Now, there's also seems to be some kind of a hint that amongst the late types as well, there might be a opposite trend, whereby as you go to higher concentrations, the fraction of stellar mass increases as opposed to dark matter. And so what we're thinking there, a very preliminary, our early interpretation of these trends is that perhaps this might be telling us something about the combination of dark halo response and feedback during galaxy formation. For instance, high C28 galaxies, early type galaxies, you have a more concentrated stellar body or stellar component. And invariably we would expect that would be associated with a larger concentration of the feedback from supernovae and so on and so forth. Yet they seem to still have not, perhaps they have retained more dark matter. Maybe as a result of the concentration driving upwards, that the dark matter got dragged in. And so this might be a sign that up here we have more adiabatic contraction than down here. Okay, so I'll just conclude briefly is the results from our study of the stellar mass function, stellar mass density profiles, and stellar mass dynamical mass relation are that we find the global environment does have an impact on the distribution of stellar mass. We find that clusters seem to host more massive galaxies than the field. Mass-to-light ratio doesn't seem to strongly vary on average with radius within the galaxies. And finally, that the plots of the dark matter fraction versus structural quantities maybe suggest that there is a trend in the coupling of feedback to halo response as a function of structural parameters and galaxy type. And with that, I'll leave the floor to questions. Thank you.
Hi, Joe. Just have a question for you. When you were doing your mock catalogs, it looked like some of your relations when you were trying to do the true to they had some sort of like consistent, like maybe I think one of them had a steeper slope than 1-to-1, and some of them had subsequently like lower than the 1-to-1, but similar 1-to-1 slope.
Mm.
Have you looked into whether like you could use those trends to sort of correct, like come up with sort of a correction term for people who are actually have observed mass to light and want to use the true mass to light ratio?
Not yet, no, but that's a good idea.
That's all.
How do you normalize the loss of stellar mass function of your cluster? You don't know the volume, right?
Yeah, that's right. So this scaling is arbitrary. It was just I wanted to show you on the same plot. What does the relative shapes?
Excess of bright galaxies is an assumption, not a conclusion.
Well, the fit of the Schechter function does give us a higher characteristic mass. This isn't like being.
Now you will have an excess of small galaxies instead of excess of big galaxies. Whatever you want.
Yeah, it brings it down to a deficit of small.
That's right. It'll be the opposite. We've assumed, yeah. You're right, that's right.
I have a very general comment, Steve. nowadays, of course, observers always convert the velocities into stellar mass and using some assumptions, and you're absolutely right. One has to be very careful about that. And actually, this sometimes this actually is a big problem for theorists, because when we make predictions, we use even kind of IMF or whatever, and then we have to convert, and also we have to correct for the volume. For example, we don't have a mass limited sample, and we have only magnitude limited sample, right? So my suggestion for observers is that it's good to present everything in terms of stellar mass, but please also present things in direct observers like the velocity. And actually that makes life easier for one.
Much more. How you predict the velocity?
But then I know one kind of assumption I made. I made assumption with this IMF.
Look, it's the same with the stellar mass. You make the same assumption.
Yeah, but that part is theory. Spectral intensity model, IMF, all is a theory. And then I can change this, and
I mean, the problem is either way you go, you've got this big black box
yeah.
with all these uncertainties and assumptions.
Yeah,
you go
but
this way or this way, and you're still.
Well, but there's an additional pain in the ass, which is that people make different assumptions, and then,
Yeah.
having had the experience of having to cull data from the literature, and then having to deal with the fact that like 10 different CO X factors were assumed.
Exactly. So why don't you just present, this is the observation. The theorist, if you want to do this, you have to choose your own conversion or your mass to light ratio, and that's an uncertainty.
Well, no matter what you do, you don't have to go from dark matter, which is what you predict, to baryons. So as Charlie's saying, whether you approach it this or that way,
Well,
you have to
the
understand.
theorist's work should also go a step forward, not only just in terms of stellar mass or star formation history, but also convert that into observables using that
It's the
assumed.
same recipe.
Yeah.
That's right. Well, that's why you need to read Joel's paper.
Okay, I think we'll discuss this over lunch. So let's thank all the speakers for this morning.